Alright, let's start here. During high intense exercise, we get an accumulation of proton, which leads to metabolic acidosis. As proton increase, pH drop, and this begin to impair muscle function. So the question is, what does the body do? The body use buffer system to bind or remove proton in order to resist the drop in pH. Why is this important? Because buffering helps to delay fatigue, maintain muscle contraction, and most importantly, it allows us to sustain high rate of ATP production. And this is the key idea. Buffering capacity determines how long you can maintain high intense effort. Performance is typically limited by acidosis, not alkalosis. So if your body adapt and improve its buffering capacity, you can tolerate more metabolic stress, especially during glycolysis dominant exercise. In other words, greater buffering capacity lead to better anaerobic performance. So pause the video and think about it and choose your answer before moving on. Which type of training would most improve buffering capacity? Now let's think about this question. What actually limit sprint performance? Energy or pH? At first, many people think it's simply a lack of energy. But in short duration, high intense exercise, energy supply is usually still available. The bigger issue is pH, specifically proton accumulation. As proton builds up, pH drop, and this interferes with key process like muscle contraction and enzyme activity. So even if you still have a fuel, your system cannot continue producing ATP at a high rate. This is where buffering system become critical. Buffering allows the body to manage proton, so glycolysis can continue even under acid condition. So the key idea is sprint performance is often limited by pH, not energy availability. So if buffering capacity improve, what happened to sprint performance? Now let's go one step deeper. A very common question is lactate causing acidosis? Many people assume that lactate is the problem, but that's actually not correct. The real source of proton comes from ATP hydrolysis. ATP plus HDO become ADP, inorganic phosphate, and proton. So every time ATP is broken down, it produces proton. So during high intense exercise, when ATP turnover is very high, we get proton accumulation. That's what drives acidosis. Now, what's about lactate? Lactate actually play a different role. Pyruvate with NADH and proton become lactate and NAD+. In this reaction, lactate formation consume proton, not produce it. So instead of causing acidosis, lactate actually help reduce it. This is a major shift in understanding. Lactate is not the problem, it's part of solution. So if ATP turnover increase, what happened to proton levels? Now let's bring this all together. The body uses buffering system to manage proton during high intense exercise. The main one are bicarbonate and phosphate, proton phosphate. And their role is simple. They bind proton to help limit the drop in pH. Why does this matter? Because buffering helps to delay fatigue, especially during high intense exercise, and importantly, capacity can actually improve with training by about 12 to 15%. Now here's the key takeaway. Lactate does not cause acidosis, the proton come from ATP hydrolysis. So we need to rethink this. Is lactate the problem or is it actually part of the solution? Now let's clarify one important point. Does lactate build proton like bicarbonate ion? The answer is no. Buffering system like bicarbonate and phosphate directly bind proton to stabilize pH. That's what define a true buffer system. Lactate is different. It does not bind proton directly. Instead, lactate is produced through a reaction that actually consumes proton. So the roles are different. Buffer bind proton. Lactate help reduce proton through metabolism. This is the key takeaway. Lactate is not buffer, but it still help reduce acidosis in a different way. So pause the video, think about it, and choose your answer before moving on. Which one directly bind proton? Buffer system or lactate? Now let's look at what happened to proton during high intense exercise. Inside the muscle, proton accumulate due to ATP hydrolysis. So what does the body do? Lactate and proton are transported out of the muscle cell through MCT transporters. This is important because it helps reduce intracellular acidosis and maintain muscle function. But the process doesn't stop there. Once in the blood, proton combine with bicarbonate. So proton with bicarbonate ion become CO2 and water. The CO2 is then removed through the respiration. So if you think about the whole system, muscle, transport, blood buffering, breathing, all of the work together to support continued high intense performance. So what would happen if proton could not be transported out of the muscle? Now let's simplify this idea. Lactate and proton efflux actually protect the muscle from acidosis. Instead of staying inside the muscle, proton is removed from the cell. This is critical because high level of proton would otherwise disrupt ATP production and muscle contraction. So removing proton allows the muscle to continue producing ATP at a high rate. Also notice this, lactate is not trapped in the muscle, it's actually transported out. This transport through MCT is not a problem, it's actually a protective mechanism. So the key takeaway is lactate transport help protect the muscle, not harm it. Now let's connect this idea to a bigger picture. The same buffering principle apply here. Proton bicarbonate ion become CO2 and water. This is not just happening in your body, it's also happening in the environment. For example, in the ocean, CO2 from the atmosphere dissolve in water and form carbonic acid. This increases proton concentration, leading to acidification. So the same chemistry we see in muscle is also happening on a global scale. The key idea is simple. Buffering system try to manage proton, but if the system is overwhelmed, pH will drop. So pause the video, think about it, and choose your answer before moving on. What happens if CO2 continue to increase in the system? As CO2 increase, more of it dissolve and form carbonic acid, which then produce proton. So we get more CO2, more proton, lower pH. In other words, the system becomes more acid. Now you might wonder, can being more fit reduce CO2 in daily life? To a small extent, yes. A trained individual may rely slightly more on fat oxidation during low intense activity, which produce a little less CO2. However, the big picture is this: you still need to produce ATP, and that always produce CO2. So fitness does not meaningfully reduce total CO2 production. The key takeaways here: CO2 accumulation drive acidosis, and fitness does not eliminate that. It's only change how energy is used. Now everything comes together. Why do we breathe harder during high intense exercise? It's not just about needing more oxygen. During high intense exercise, buffering reaction generate CO2. That CO2 must be removed. And the only way to do that is by increasing ventilation. Right. So you breathe harder to blow off CO2, not just putting in oxygen. No. This leads to an important point. providing extra oxygen does not solve the main limitation. High intense performance is primarily limited by ATP turnover rate and acidosis, not oxygen availability. That's why in training, we focus on improving buffering capacity and glycolytic function, not simply oxygen supply. So the key takeaway is you breathe harder to remove CO2, not just to get more oxygen. So is breathing harder driving more by oxygen demand or CO2 removal? Now let's finish with the key idea. Acidosis, protein accumulation, not lactate, limits performance. During high intense exercise, ATP is broken down rapidly, which leads to proton accumulation. As proton build up, it interferes with muscle contraction and reduce your ability to keep producing force. That's what limit performance. Now, what about lactate? Lactate formation actually consume proton, helping to reduce acidosis. So again, lactate is not the cause of fatigue. It is part of a system that help managing it. So that's why if you want to perform more repetition or sustain high intensity longer, you need to improve your ability to control acidosis. This is done through buffering system, glycolytic adaptation. So the final takeaway is performance is limited by proton, not lactate. So what should the training focus on? Reducing lactate or managing proton? Now here's an important mistake people make. After intense exercise, they often just sit down and rest completely. But that's not the best strategy. Instead, you should keep moving lightly. Light movement help maintain circulation and ventilation, which allow faster removal of CO2 and proton. This leads to quicker recovery. Think about dogs. Dogs don't sit still after activity, right? Don't sit still after activity, right? They pant. Panting helps regulate CO2 and body temperature, not just oxygen intake. So the key takeaway is recovery should be active, not passive. So light movement help clear metabolic byproduct and restore the system more efficiently. Which is better for recovery after high intense exercise? Complete rest or light active movement? Now let's connect buffering directly to performance. Buffering becomes especially important during high intense effort like recent training or the final stage of endurance event. At that point, proton accumulation increase and buffering capacity become a key limiting factor. If you have a greater buffering capacity, you can delay fatigue and maintain performance under stress. Now here's an important insight. Performance is not determined by max alone. Some elite athletes perform at a very high level even without the highest max. One possible reason is their superior ability to manage acidosis, in other words, better buffering capacity. So the key takeaway is the ability to tolerate and manage proton is critical for high level performance. So what matter more in the final stage of a performance, oxygen delivery or buffering capacity? Now let's finish with an important question. Can two athletes uh, with the same max perform differently? The answer is yes. max represent your capacity, how much oxygen you can use, but buffering represent something different. It's your ability to sustain that capacity under stress, especially when proton begin to accumulate. So even if the two athletes have the same max, the one with better buffering capacity can maintain performance longer and at higher intensity. This leads to the key idea. High performance is not just about oxygen capacity, it's about tolerate to metabolic stress. So what determines performance at the limit is capacity or the ability to sustain it. Let's quickly review what pH actually means. So pH is defined as pH negative log of proton concentration. This means pH is logarithmic, not linear. For example, pure water has a proton concentration of 10 minus 7, which give a pH of 7. Lemon juice has a proton concentration of about 10 minus 2, which give a pH of 2. So even though the number looks small, the actual difference in proton is huge. Now let's apply this to exercise. At rest, muscle pH is about 7.1. During exercise, it can drop to around 6.5, and in severe case, even 6.4. That may not look like a big change, but because pH is logarithmic, this represents a large increase in proton. Even a small drop in pH means a tenfold increase in proton concentration. And that's why it matters. Proton directly affect enzyme function and muscle contraction, which means fatigue is not just about running out of energy. It's a regulation problem. That's why pH tightly controlled in the body. And during recovery, what we are really doing is buffering proton, removing proton, and restoring metabolic stability. So the key takeaway is fatigue is not just about energy depletion, it's about maintaining control of the metabolic environment. Let's finish with one final concept. Many people think fatigue happens because ATP run out first, but that's not what actually happened. ATP is tightly regulated, and its concentration remains relatively stable. Instead, the body protects ATP. The first line of defense is phosphocreatine or PCR. PCR breaks down rapidly to help maintain ATP level through the creatine kinase reaction. So what you are seeing is not depletion, it's actually protection. PCR is essentially sacrifice to prevent ATP from dropping. And ATP is not maintained by phosphocreatine alone. It's also supported by glycolysis and mitochondrial respiration. So the key idea is this. Fatigue does not begin when ATP runs out. It begins when the system can no longer maintain ATP stability. So final takeaway is performance is not about how much ATP you have, it's about how well you can maintain it. Thank you very much.